So welcome everyone to the afternoon session. Before we start, just a reminder that there is a group photo at 4 right after this lecture. So I hope everyone is wearing their best clothes. There's going to be no time for changing. So, okay, so welcome back. And we are very pleased to have Nathan Dogra from King's College London. So this is the last mini course which will start now. And he's going to talk about Chaboti-Coleman-Kim method from theory to practice. Over to you, Nathan.
Thank you. Thank you very much to the organizers for inviting me and giving me the chance to talk about this subject, which I love. It's really a pleasure and an honor to be able to be here in this wonderful place and to be able to be giving these talks amongst all these other speakers. So what I want to talk about is a subject which maybe historically has had a reputation for being somewhat technical, and hopefully I can make some parts of it less technical. And one way that I can do that is by encouraging those of you trying to follow to ask me questions during the talks and also afterwards. I'm going to try and have lots of exercises which you can think about during the talk as well or after. So the goal of the Chaboti-Coleman-Kim method is to, a bit like in the Chaboti-Coleman method, is to construct some kind of transcendental functions of some kind of p-adic analytic nature which vanish on rational points. And the constructions and the definitions can be quite elaborate and quite intricate. So maybe before I go into the details, I just want to give you the kind of slogan of the method, I would say, which is actually probably quite a misleading thing to say in a conference on rational points on modular curves, because it sounds like a slightly more impressive claim than it is. So the idea behind the Chaboti-Coleman method is a variant of an idea which has appeared in other areas, that Diophantine finiteness results should be a consequence of the fact that rational points are special points. So, so maybe I should just say warning. You'll see in a second. So special points here doesn't necessarily mean CM points. So one of the big kind of open problems in rational points on modular curves is that for certain class of modular curves, it's conjectured that all the rational points are CM points, which are sometimes called special points, and we don't. that's a slightly different kind of special from what I mean here. It isn't necessarily CM. So rather what special points means is that we'll want to construct some kind of relations, some kind of transcendental functions. Sorry, this is too high. Which in this case will be p-adic, but in other contexts this has come up in a complex analytic set to some affine space. And then actually we construct some subvariety of that affine space, which actually both of these things, even though the map is defined over QP, both of these things can be defined over Q and can be kind of given in some kind of intrinsic way, such that this, as I say, this is into some p-adic. So this is for X over Q, e.g. a curve contained in W of QP. Now, actually, this is not quite true. So even in the Shabaty-Coleman method, we don't quite do this because the Shabaty-Coleman method actually gives you a subvariety defined over QP. But the specialness, which we want to exhibit, is going to be something which is defined over this is, sorry, it's introduction. This is something we can do not for x of q, but we do it for x to the n. And it might seem odd to think that it's somehow easier to kind of study n tuples of rational points than just to study rational points. Why should it be easier? You know, rational points on x to the n are the same as n tuples of rational points on x of q. But actually, in terms of this kind of philosophy of rational points being special points, turns out the behavior is very different. And so actually this idea of that Diophantine finiteness of x should come from special properties, specialness of x to the n, actually goes back to an idea in the Zilber-Pink conjecture. This is some kind of very different a priori subject about special subvarieties of Shimura varieties. The very general conjecture, but in particular, one very special case of this conjecture concerns subvarieties of abelian varieties. And when they intersect with infinitely many proper subgroups of an abelian variety. So, I mean, why? So one example of why it's good to study x of n, why x of n might have some special properties is, suppose, let's say that J is the Jacobian of x. So let's say, suppose x is a curve. And let's say, suppose that the rank of J of Q is R. Then we have the following specialness property of the rational points of J and also the rational points of X, which is that then every point in J to the n of Q, for all n bigger than R, is actually contained in a proper subgroup of J to the n. A proper subgroup. Now, why is that interesting? Well, the Zilber-Pink conjecture is exactly about this kind of situation, although that's not what I'm going to talk about now. But I mean, the point is that, you know, a priori, this doesn't help us. So in particular, x to the n of q, which is the same as x of q to the n, is contained inside infinite union of or even just over the complex numbers. Right. J of C to the n. And so yeah, the Zilber-Pink conjecture would then imply that this meant that this had to be not Zariski dense in X, which would imply that X of Q was finite. So, I mean, if you could make this method effective, this would give an effective way of finding the rational points on any curve. I mean, we can't even prove this conjecture. But the Chabot-Coleman method is kind of like a p-adic version of this. Where again, we're going to have some affine space defined over Q, and then we're going to say that construct some transcendental map and then show that the rational points actually lie in a subvariety, which again, we can describe completely explicitly and is defined over Q. And again, we do this for n tuples, but here we actually have to impose a rank condition. It's like, so X as before. But now we suppose that the rank is less than the genus. And then let's consider and J as before. Let's consider this map, which came up already in Samuel's lectures. From the p-adic points of the Jacobian to the tangent space of the Jacobian at the origin. And remember, this is just isomorphic to UP to the G. So then log J of, if we take the n tuples of this, or let's just take n to be G, so take this G tuples of this, so inside, oh, sorry, I've gone too high again. So this is just G tuples of G tuples, so we could just think of this as G by G matrices. Is contained as the property that log J of J of Q is now contained inside the set of rank less than G points, which under this isomorphism, we can think of as just being given by the equation determinant equals 0. So there's actually a subvariety of Lie J, just even defined over Q, when we take it to the Gth power, which contains all the rational points of J to the G. And then to go from this to actually finding the rational points on X, which is what we care about, you kind of have to find G minus 1 independent points on the Jacobian. So then, I mean, there's a generalization of this Chabot method called quadratic Chabot, which, roughly speaking, the idea is that you replace the condition, I mean, it's somewhat more general than this, but replace R less than G with R equals G, and you replace a map to UP to the G with a map to UP to the G plus 1. And then you actually have to replace G tuples with something much bigger. So in general, I think something like this. off the top of my head just now. And the reason is because this fact really used some kind of linear property of these analytic functions, these logarithm functions. And now we have something which is not linear, but is kind of degree 2, and we can essentially think of it as being quadratic, and then this g times g plus 1 over 2 is coming from considering the space all bilinear forms on the Lie algebra. And then, to some extent, I'm going to talk about a more general framework even than this. So then you replace log j with certain Kalman functions or iterated Kalman integrals. And you hope to show the existence of some kind of polynomial relations. And you can say, in terms of the degree of these iterated Kalman integrals, so how much you iterate, you can say something about what the degree of these polynomials should be. I'll give some examples of that later, hopefully. So that's kind of the plan of action, is to explain this passage from here to there. And the first thing we're going to need to do is to explain what these functions are, in particular what iterated integrals are. And then after we've done that, then we can define this map log, this kind of generalization of log j. And then finally, we'll explain how you can hope to kind of, in some cases, show the existence of these relations, which will in some sense kind of bring us back to the kind of flat descent calculations that we saw earlier today. So to explain what these functions are, we have to think about how to talk about differential equations in a kind of algebraic geometry-ish language and how to work with them. And that's the notion of flat connections. So let's let X, future reference, be a variety over a field K, which in most of the definitions doesn't have to be characteristic 0, but the behavior is quite different if it's not. So let's just say that it's of characteristic 0. And let's say V, the vector bundle on X, so a connection V, this is strictly speaking relative to K. This is really not a structure just on X, but is actually a structure on the map from X to spec K. The morphism achieves such that it satisfies something called the Leibniz rule. So for all open sets, for all sections of V on your open set, and all functions on U, when you apply your connection operator nabla to f times s, it's equal to f tensor df plus f times nabla of s. So just a remark. Sorry, I've done it again. Just to emphasize, it's really built into the definition. This is not an OX linear map, so we're not working in a category of this morphism is not living in a category of OX modules, but it's kind of almost OX linear in the following sense. Clearly, this condition is imposing quite a lot. Well, sorry, maybe first of all, give an example. So we're going to say that the vector bundle, which I'm going to usually call a VB, V is constant, or maybe if I'm feeling more judgmental, I might call it trivial, if the V is isomorphic to OX to the N. And maybe sometimes I'll be sloppy and I'll implicitly be choosing a trivialization when I say that. And then I suppose, yeah, here I'm choosing a trivialization. Then on OX to the N, we can just take the connection to just be D. Connection. So yes, we say that the pair of the vector bundle and the operator nabla is a connection on X over K, which I'll also call the constant or trivial connection. So that's one example of a connection on a trivial vector bundle. But here's an exercise that you have a trivial vector bundle. And every connection on V is of the form V plus lambda, where lambda is just a matrix of one forms. And maybe I should also say, and not only is everyone of this form, but these are, and it's really a one-to-one correspondence. Every such lambda defines a connection. The condition determinant equals I guess in terms of this map to this, I mean, it's different because I said that it's this tuple. So if this is N, then it's, you can think of it as a map into N by G+1 matrices. I think the correct thing to do would probably, there's a certain kind of quadratic, there's a degree 2 map just from this variety over Q to sorry. This, and it's then it becomes a determinant equals 0 here. But I mean, roughly speaking, the first two g functions that you get are kind of like your linear logarithm functions, and then the last one is like a height function. And rather than it being a linear relation between these, it's a relation between this last height function and all the possible bilinear forms in the other ones. So it's not a linear relation between them, but it's a linear relation between them in some kind of weighted degree 2 sense. Thanks. Maybe I could even actually give the simplest example of integral points on an elliptic curve. When integral points on an elliptic curve, then the two functions are log e and the local height at e. And the statement is that there's a linear relation between these two functions. So that's sorry, not between these two functions, but between this one and this one. And then in general, when you're dealing with higher ranks, rather than just considering the square of this, you consider the basis of the literally, sorry, yes. Yeah, sorry, it would maybe it would have made more sense to have done the rank 1 case. So if your vector bundle is just OX, then D is just the differential. Yeah. And then for this to the n, it's just this to the n, which is the same as thanks to this tensor arrays. Yes. So yeah. Thanks. Where do I? Yes, so I wanted to maybe just make a little remark about how I think about connections, or at least how I think about them, which is that it might be kind of tempting, if you're very familiar with thinking about vector bundles, to think that this connection is just some kind of decoration on a vector bundle. So if I want to kind of understand what all vector bundles with connection look like, I just kind of think about vector bundles and then add this extra information. And that's true in a sense, but there's one very important difference, which is that kind of between how these categories behave, but they're not categories yet because I haven't defined the morphisms, but I'm just about to. I'm going to be a bit vague, but basically in all the situations we're going to talk about, with connections, vector bundles with connection. Yeah, sorry, usually this pair V nabla is called a vector bundle with connection. I'm often just going to call it a connection. You don't lose information by working locally. So more precisely, typically, depends a little bit in the context you're working in, but in the context we're working in, if you have a vector bundle with connection defined on an open set, then if it extends to a larger space, so the closure of that open set, that extension will be unique. And this is completely different from vector bundles. Vector bundles are locally trivial. So, I mean, obviously, often you do local calculations, but you can't say, I'm going to study vector bundles by just looking at them near a point, because then they would all be trivial. But with connections, they really are, you really can study them locally. And then because vector bundles with connection, because vector bundles are locally trivial, that means you can always study a connection just by looking at this matrix lambda. So it's really not a bad idea to just think about a connection as being a matrix of one forms, is what I'm trying to say. So I said it was a category, so it should give you the morphism. The morphism of connections. So V1 nabla 1 to V2 nabla 2 is a morphism of vector bundles. Which respects the connection structure, which means that this diagram commutes. That's why this is F, and this is F tensor 1. And so follow an exercise from the last exercise. So suppose that V1 is just OX to the N1 and V2 OX to the N2. So that nabla I is D plus lambda I, the notation above. Then what's a morphism of connections? Well, first of all, it's a morphism of vector bundles. And a morphism between the trivial rank n+1 vector bundle to the trivial rank n+2 vector bundle is just given by a matrix. Of global functions on X. And then how does this diagram fit into the picture? So the condition will be that if I do lambda 1 and then I do F, that's the same as doing F then doing lambda 2 plus the differential of F. This is an identity in matrices of one forms. And to reiterate the remark I made just a second ago, this is in the same way that this lambda is really a good way to think about connections. This F and this equation is a good way to think about morphisms between connections. In particular, this identity is actually the heart of studying, for example, isomorphism classes of connections on a vector bundle. So I said at the end of this whole story, we want to actually get some functions out of this. So what are the functions you get from a vector bundle? So the functions are horizontal sections. So it's the section. Which is killed by nabla. And we write the set of horizontal sections. So here are some more exercises. The horizontal section is the same morphism of connections from the trivial connection to V. Let's see. Yeah. This one? Mm-hmm. Ah, yes, yeah, no, so it's it's lambda 1, then F, and then lambda 2, and then this one is the other way around. Oh, sorry, that's just me not knowing how to, yeah. This happens every time I try and use Magma as a defining measure. Is it? Sorry. Yeah, thank you. Does it make sense now? What's okay, good. Yeah. Okay, so the second one is that you can add and multiply by scalars horizontal sections. So this is a K-vector space. Vector space. Maybe we're sticking this one intermediate one as well, which is that there's a K-vector space, and if so for the trivial connection, so then you have the global section X, sorry, 1, with a K basis of okay, well, actually, maybe I'll do this exercise. Yeah. Wait, for which one to be true? 3? Well, I guess. Yes, so maybe my varieties are geometrically connected. Yeah. Thanks. Yeah, so I mean, what I want here is I want that kernel of B is okay. And finally, the K dimension of the space of horizontal sections is less than or equal to the rank of V with equality if and only if V nabla is constant. So yes, as as Eli pointed out, this statement has some assumptions on X to do with connectedness. I mean, this is also something where a reason to restrict to the characteristic 0 case. So in characteristic P, the kernel of D can be very big. And that's one reason why connections in characteristic P are interesting, but they behave very differently. Okay, so I said that horizontal sections will be the source of the interesting functions which we're interested in, but as I've defined them, they're just algebraic functions. So that doesn't seem to give us the transcendental functions we want, and the reason is that you can consider connections in other categories than algebraic categories. So, for example, you consider connections on formal schemes. Sorry. So maybe it'd be better to say we'll also consider connections on formal schemes over K. Maybe if K embeds into the complex numbers, we could consider the analytification and consider connections in that category, rigid analytic spaces, and so on. So in all of these cases, you can define the analog of a vector bundle with connection. And the only thing which is slightly different is you just have to define what you mean your sheaf of differentials to be. So typically, the special functions that we consider will come from starting with a connection on our algebraic variety, an algebraic connection, and then considering horizontal sections either formally or analytically. So I'll give some examples in a second, and this will hopefully make a bit more sense. Formally or analytically. And actually, in some sense, starting with an algebraic connection and then considering it over one of these other categories actually gives you a different language for thinking about connections in the first place. For example, you could look for formal horizontal sections, and then those would give you some kind of transcendental functions, which you add into your ring of functions. And then you could think of that bigger ring that you get just as an objective algebra, just as a K algebra, except that it now has this added property that you have this differential, so which describes this differential equation which the horizontal section satisfies. And so that would be kind of thinking, essentially, about this as an objective differential algebra would be. You can also think of local horizontal sections topologically, say over the complex numbers. So you could take complex analytic horizontal sections. As we'll discuss a bit later, this gives you something called a local system. Once I've put another word here, which I'll describe shortly. And so that essentially lets you kind of think about this category, which you were thinking about geometrically so far, or rather in the language of algebraic geometry, in terms of topology. And these three different perspectives are all useful in different ways. So let me give an example of, well, I mean, maybe I'll just give the kind of simplest non-trivial example, which isn't really actually in the spirit of this course, but it's worth saying, which is that you just take the affine line, you take your vector bundle to be OX, so then we can describe, as we said, we can describe the connection as d minus lambda, and I could just take my lambda to be dx. So then, actually, sorry, I think my convention, I'm going to take it to be minus dx. So a horizontal section I should have said this. I said that I wanted to think of everything locally in terms of lambda, but I didn't say what a horizontal section was in terms of lambda. But horizontal section for d minus lambda is just a solution to d g equals lambda g, where lambda is an n+1 tuple of functions. So this is in general. And in this case, that means that is a solution to dg equals g times dx. So there are no algebraic, no non-zero algebraic horizontal sections. But we could work formally or complex analytically, and then we'd have a solution that was the exponential function. And this kind of dictionary here is essentially saying that, if I think of the algebra I get with a differential coming from just adding a new function to polynomial functions, which is the exponential, and specifying that it satisfies the usual differential equation, that's the same as studying this connection. So actually, it's still here. So I'm sure everyone here has their own favorite vector bundle with connection. This is my favorite vector bundle with connection. If it wasn't for this vector bundle with connection, I wouldn't be here today. So it's not the, it's a slightly prosaic one in some ways, but it means a lot to me, and that's trivial vector bundle of order 2. I'll go wrong with the trivial vector bundle, and d minus lambda, where lambda is just the matrix 0, 0, 0, dx over x. So exercise, algebraic solutions are given by 0, lambda for lambda and k. But we can also look at formal solutions. And then this would be given by lambda mu plus lambda times log x. And yes, again, somehow the information contained in this connection is also kind of contained in this transcendental function. And then, as we'll discuss when we discuss analytic continuation and monodromy of connections, it's also kind of contained in the analytic continuation of the logarithm winding number. It's a very simple example, but it actually contains almost all the features we'll be interested in, except for the fact that it's not quite non-abelian. So later, when we want to get non-abelian, this will be go slightly further than this. So just this, isn't maybe strictly necessary for us because we'll be mostly interested in the one-dimensional case where this condition is automatic. But I feel like I ought to explain what the word flat means. Flat, also sometimes called integrable. So in the one-dimensional case, so maybe I should say, this is immediate, so you can ignore this if you're just interested in curves, which we mostly are. But what is it in general? The point is that we want to I said that we want to be able to think of our flat connections in terms of formal or analytic solutions around a point. We want to have a basis of solutions around a point, which is equivalent to having a trivialization around that point. So we want to be able to solve. So locally, our connection will be given by d minus lambda of at least a formal solution to the f equals lambda times f. Playing with the microphone. Say around some x in x of k. So what does that condition amount to? Well, suppose that formal completion of x at x is isomorphic to a of little x1 to little xn. Then this has basis dx1 to dxn, and we can write lambda as some, say, sum I equals 1 to n, lambda I times dxi. Whereas lambda I is now, well, I guess I've already taken n, so it's 1m. Let's say this is a rank m vector bundle in this ring I'll call R. So the flatness condition is saying that we want this equation here to have a solution in R. But basically, this the flatness condition comes in because this is actually going to be n different equations corresponding to different dxi's. So let's say exercise. R is equivalent to, well, I guess I've just explained it, saying that df by dxi equal to lambda I. Okay, but now we could differentiate this identity again, say with respect to xj. And that should be the same as differentiating f with respect to xj and then with respect to xi. So that means we should get a condition which we can actually write without describing f, just in terms of the lambda i's. I guess we want f to exist. Actually, we want more than that. We want a basis solution, so we want it to be in GLM of R. It's equivalent to saying that it's a basis of solutions. Then we have this identity. And this is the condition of flatness. One way of writing the definition of flatness. And as I said, if n is equal to 1, then this condition is immediate. That's for all ij. So I've given a very kind of apparently coordinate-dependent definition of flatness. Now I'll give a coordinate-independent definition, which is convenient because it allows me to then also discuss the de Rham complex and de Rham cohomology, which will be useful later. So, how do I say this without having to choose all these formal coordinates? So we'll call the de Rham complex is defined by the ith term being the ith wedge power in coherent sheaves on X over K. And we define di from ixk tends to v and I plus 1 xk tends to v by, it's not di actually, but nabla I. And exercise, might want to check the sign on this because I noticed that when I started talking today, I changed the order in which I tensed these two things. Be a possible typo there. And so, okay, so when then you can define the curvature of the nabla to just be this map from E to nabla 2 tensor V. And V nabla is flat if nabla 2 is 0. And if I haven't messed up the signs, then in local coordinates, this will be equivalent to this So when this is a silly way of defining the differential on the de Rham complex, but it so happens that I have already defined it. So this defines complex. The nabla I is usually written di. This is the de Rham complex of X over K. And remember, if X is a d-dimensional variety, then this is going to stop at omega d, because omega is going to be rank d, so there won't be any d+1 wedge powers, non-zero ones. And we define the de Rham cohomology, hi de Rham of X over K. So the general definition is rather complicated, but actually the nice thing is that in these talks, somehow because we're doing something to do with fundamental groups, we actually just care about H1 and H2. We don't really see any of the higher cohomology. And then in that case, it's much simpler. The general definition is that it's the ith hypercohomology in X of this complex. So in particular, if you have a one-dimensional variety, this complex just has two terms. So it's just hypercohomology of a morphism, which, I mean, well, in general, there's a spectral sequence which relates this to the cohomology of the individual omega i's, but in this case, that comes out much simpler. And you can use this to check that I can recover the first de Rham cohomology group of X by thinking about this group here, where X1 de Rham denotes a vector space of extensions in the category of vector bundles with connection. So giving a de Rham cohomology class is the same as giving an extension of the trivial connection by itself. You can also think of this X1 as the set of short exact sequences of vector bundles with flat connection. To equivalence of short exact sequence. And then maybe an exercise for people who, well, probably both of these are maybe exercises for people who have seen a bit of de Rham cohomology before. Suppose now that X is projective. If X is projective, then we have a Hodge filtration on the de Rham cohomology, which on H1 is basically described by the map from H1 de Rham of X over K to taking cohomology just of OX And under this isomorphism, let's say we call this star star. So this corresponds to taking an extension of the constant connection by itself, and then forgetting the connection. Just looking at extensions in the category of vector bundles. Which one? This here? Oh, this complex is not acyclic. Ah, yes, yeah, absolutely. So this is the notion of cohomology of a complex. And so that can be computed by taking an acyclic resolution, but it's now an acyclic resolution of a complex by a complex of complexes. Yes, yeah. So, I mean, roughly, I forget the exact homological algebra, but roughly, I mean, one way you can compute this is that you construct an injective resolution of get x over k by complexes, where each of the i's is injective, all the way up to the light bulb, and then you take a kind of total complex, roughly speaking, of this, and that's the cohomology of the usual cohomology of the global sections of that. Gives you the cohomology, yes. But yeah, no, you're absolutely right. It's more complicated, except if x is affine. If x is affine, then essentially because there's no higher cohomology of coherent sheaves, you can actually just take the cohomology of this complex after you apply global sections. And well, as I said, when we're thinking about connections, we can always work locally. So, I mean, that's even just thinking about this in the case of locally in the case of well, yeah, locally, or in particular in the case of an affine scheme, is already instructed. Whereas this thing here really is something which is not interesting. This one is not interesting if you're affine, because actually an extension of the trivial vector bundle by itself on an affine scheme will have to be trivial, which I guess fits with the fact. In this exercise, you should check that you have this isomorphism. And maybe I'll just give you a hint for how to do all of these calculations. I mean, I think the easiest way to maybe there's some kind of it's abstract nonsense way to think about it, but I think the easiest way is to think in terms of check cocycles, the cohomology, and charts for vector bundles. So now on to talk about the kind of topological aspects of this. Which is the notion of parallel transport. So what's parallel transport? Suppose you have a trivial connection on X. then for every k point of x, you could take the map from global sections to the fiber at x, which I'm going to write like this. And then you could do that restricted to horizontal sections. And these are now both k vector spaces. You have an isomorphism. So this is a bijective map. And that means that xy over an xk gets an iso, which I think I'm going to write as ixy from the fiber at x to the fiber at y by pulling back, taking the inverse of this isomorphism here, going down the other way. So you might think, well, you said it was a constant connection, so it's not surprising that I can identify the fibers because it's just constant. But this becomes interesting when we consider algebraic connections, which have trivializations or a basis of horizontal sections in some other more fancy category. So example, we could take the logarithm connection. On GM. So we're working over C. And then we could restrict it to C minus negative real numbers and analytify. Then V nabla becomes trivial. So maybe let's call it the analytification of that. Right. It admits a trivialization. And let's say for all xy, C is r less than 0. Sorry, this should be less than or equal to. Ixy of, let's call it lambda mu, is equal to lambda mu plus lambda times log y minus log x, where log the usual branch of the logarithm. Okay, but when things get really interesting is when we do parallel transport not on a contractible space, but on a space with an interesting fundamental group by composing these kind of trivial contractible parallel transports. So now let's suppose we've got some x over C, which could be convex analytic manifold. And let's suppose we've got a path not 1 to x of C. Okay, so then we want to define an isomorphism push forward of gamma from, and yeah, let's say sort of vector bundle connection. The fiber at X, the fiber at Y. I guess to define this, I should note something which I didn't mention, but maybe is a good exercise. So this is a good exercise, complex analytically, but also p-adically. Let's say that this is actually maybe just on a variety. Is a connection. K could be equal to, K could be QP or C here. And suppose you have some K point. And I said that you can always formally trivialize a connection or find a basis of horizontal sections. Actually, so that formal trivialization actually extends to an open neighborhood of X. So in the p-adic case, we'll talk more about the different kind of open neighborhoods that we're going to be considering, but for now we can just think of that in the topological sense of open neighborhood. And of the complex numbers, it's an open neighborhood in the usual topological sense. Yeah, so as I said, yeah, in the p-adic case, I mean, we'll talk more about what kind of open, I mean, so it will actually be an admissible open, but for now, I mean, we can just take it to be in the sense of a topological space, or p-adic ball around X. So if we now go back to our setting of this path gamma, if we can find an open cover, U alpha of X. So for all alpha, the nabla restricted to U alpha is trivial. And then using this, we can find a decomposition of the unit interval such that on each segment of that interval, our connection trivializes on open neighborhood. So I'll draw a picture in a second. So then the idea is that we just compose the parallel transports on each of these segments where it trivializes to define our map gamma star. Yes, notation is I. Rather than worrying about all the kind of cumbersome notation, let's just draw a picture. Then we have our topological space right here. And then we have some path, and the idea is that we're going to trivialize it in some collection of open neighborhoods. And then these will be our gamma T0, gamma T1, and so on. Okay. So I should emphasize that in general, I mean, what makes this construction interesting is that in general, there won't be a neighborhood of the entire path on which this trivializes. And we'll see an example of that in a second. One important feature of this definition is that if you have two different paths and they're homotopic, then they give equal functors, give equal isomorphisms. So this gives a map I1 x of c xy to the set of isomorphisms of x star b y star b. So other properties. Well, it behaves well under composition. So that means that if I compose gamma 1 and gamma 2, this, in particular, we get a homomorphism I1 x of c x to the general linear group of the fiber of V and X. So maybe I'll give an example of this. We go back to my favorite, I don't know if it's my favorite, it's just the connection which has meant the most to me in my life. But definitely top 5. This one, and we take a path from 1 to itself, then gamma star of lambda mu is equal to lambda mu plus 2 pi I lambda W of gamma by W of gamma. Z is the winding number of gamma. Okay, so maybe one other thing which maybe seems like a slightly more odd statement, but it will become very important later, is that, well, it's not an odd statement to make on its own, is that this is functorial in where if gamma is a path from X to Y, it's functorial in vector bundles with connection. obvious sense. So, I mean, we can think of X star, for example, as a functor in the category of vector bundles with flat connection on X over K to the category, which I'll call vec K, which is going to be finite dimensional K vector spaces. And so, yeah, now if K is equal to C and we're working in this analytic context, then gamma star is, rather than just thinking of this as being something defined for a specific V nabla, we can think of it for all V nabla, and it's what's known as an isomorphism of functors. And the definition of an isomorphism of functors is kind of just the two properties that I've told you that it has, that it's have isomorphisms of vector spaces, and these are functorial in V nabla. So maybe the last thing I want to talk about is the kind of strongest possible version of this statement, which is maybe due to Deligne, which is sometimes called the Riemann-Hilbert correspondence for connections. And to explain the Riemann-Hilbert correspondence in these last couple of minutes, maybe I should also just back up and say that I told you a slight lie. So I said that we can work with connections locally. In Zariski locally. We pay a price. It's kind of just like the price we paid when we, in the previous lecture, when we worked with flat Grützgrüngs locally, and then we could just think of them as Galois representations, which is that we have to think about how we actually extend them, the bits that we've removed. So basically what I said is that we can think of a connection I said we could just think of it locally, which means we could just think of it even over the field of fractions. It's not at all obvious when this extends to a connection on X. So maybe exercise. Suppose you have some omega well, I guess we could just say it's A of X over K, X, a nice curve. Then D minus, so I guess strictly speaking, I mean this, and if you can do a generalization of the logarithm with this omega, you replace dx over x by this omega, and this extends to x. That's the condition. If and only if, for x and x of k, I guess we a bar. The residue at x of omega is equal to 0. So to finish up, I'll just tell you what the definition of the residue is. So dx is a parameter, and omega equals to some power series expansion. The residue of omega, a minus 1 coefficient. So I guess, for example, the logarithm connection didn't extend to the whole of P1 because the residue of dx over x at x equals 0 is 1. Oh yes, well actually one thing I should have said, so there's a written version of my notes on my webpage for this lecture, which discuss the Riemann-Hilbert correspondence. And I think I'll stop there for today.
Are there any questions or comments?
Sorry, what was I describing? Yeah. Avid. Yeah. Well, it's essentially, so I said if you had the constant connection, so on the constant connection, we can identify all the fibers canonically with just k to the n at all k points. And then the map is just that identification. Yeah, so I suppose, maybe I could have explained this better. So horizontal sections are somehow contained in the information of trivialization, and a basis of horizontal sections is equivalent. So yeah, actually computing this is basically equivalent to trivializing your connection. But I guess, this sometimes this information is a more convenient way of packaging that.
Any other questions or comments? If not, let's thank the speaker again.